previously you saw a video of two different types of simple harmonic motion. There are many types of simple harmonic motion, but you saw spring, a mass oscillating on a spring, and you saw masses oscillating like a pendulum back and forth. We're going to put some definitions and more specific type of information about simple harmonic motion. We'll be referring to the spring oscillating up and down on a mass, or even horizontally oscillating on a spring, and also masses oscillating back and forth like a mass hanging from a string on a pendulum. So we'll be referring to that video as we go through some of this information. First of all, let's talk about some definitions and some basic information about oscillation. Now you can pause this video and write these notes down. It's important that you write them down so you can have them as a quick reference. Some definition: periodic means object oscillates back and forth over the same path, each cycle taking the same amount of time. That means it's periodic, like the mass oscillating on a spring going up and down. It goes through one complete cycle, the same time every time it goes up and down. Equilibrium position is the length of a spring or the mass on a spring. Or it can be, now I'm using a reference to a spring here, but it can also be a mass on a pendulum or any other object that's oscillating back and forth. So it's the length of a spring or position of mass when no net force is acting on it. Notice that says net force. That doesn't mean there aren't any forces acting on it. That just means there's no net force. Anything in simple harmonic motion has to have a force acting on it or forces acting on it. Just in equilibrium, all those forces add up to be zero. There's no net force on it. A restoring force. What happens because this object is changing its motion, like a mass going up and down and a pendulum going back and forth, there always has to be a force on the mass that causes it to move back to its equilibrium position. So that's the restoring force. And the restoring force is always in the opposite direction of motion. We'll look at that when we get to an equation. Now, let's take a look. We've had Hooke's law before, but we're going to look at it in a little different light as far as simple harmonic motion. So we have a mass on a spring. You should draw this diagram. This is a mass. This is a spring. There's a mass suspended from that spring, and it's not moving, so it's in equilibrium at this position right here. At equilibrium, we call that x equals 0. Okay? Usually up is positive and down is negative, so remember that. So then if I pull this mass down to some position, we'll call this negative x below its equilibrium position, then as we stretch that spring is going to apply a larger force going up, causing a net force to be in the direction of its equilibrium position, causing this mass eventually to start going back up this direction. Now it's going to pass that position because it's moving. As it passes that position, it's going to keep moving until the spring compresses, and then there's going to be a net force from the compression of the spring and the gravitational force pulling it back down this way. So this mass is going to keep oscillating up and down. There's an equation, Hooke's law, F equals negative kx. The reason that negative is there is because this is net force that's being applied to the mass is always in the opposite direction of motion. Okay? You can always think of it that way. Sometimes I'll leave that negative off because the force is simply a magnitude, and depending on where it is, the direction of the magnitude depends on how you draw the diagram. So some other definitions. Displacement is the distance from equilibrium position. So this displacement down here is negative x, this displacement is positive x. Amplitude is the maximum displacement from equilibrium position. As this mass moves down, it's always some distance from its equilibrium position, but the maximum displacement is called the amplitude. So this amplitude is negative x this way and positive x this way. A cycle is one complete cycle to and fro. So if the mass starts, we're starting the motion here, then the one cycle is from there all the way back until it gets to that position. Or if we start here, it's from the time it goes up and back down to its position. Now if we start somewhere in the middle, like this position here, and this mass is moving down, so it goes down, back up, we have to go up to here, and then when it's moving back down again, because at this point it can be either moving down or up. We have to go through one cycle until it's moving in the same direction at that position. Some terms that we've had before is a period, is the time for one cycle, usually in units of seconds, or it can be any unit of time. Frequency is the number of cycles in 1 second, or number of cycles per second. And the period is the inverse of the frequency. The frequency is the inverse of the period. Usually period is in seconds. Frequency is 1 over second because it's the inverse of period, which can be written as second to the minus 1, which is the same thing as a hertz, H-E-R-T-Z. And that's abbreviated H-Z for that. So this is just some basic information. Some of it's review, but we need to have that foundation to go on to the next type of analysis. Let's go into page 2. What we're going to do here, if you remember, we're going to use the oscillation of a mass on a spring. So remember that video, we have mass suspended from a spring and it's oscillating up and down. We're going to start over this area. We're going to take this space right here. We're going to split it in half vertically, down like this. Then we're going to split it in half horizontally, pretty much like this. Okay? And we're going to call this position 1, this position 2, this position 3, and this position 4. And we're going to draw a mass oscillating on a spring. So we're going to start with a spring where a mass suspended from that spring. Just think of that video that we had. We had a 500 gram mass suspended from the spring, and initially it was at rest, but we moved it some displacement and it started oscillating up and down. So imagine this mass moving up and down, and it's at this point right here. And we'll say when it's oscillating up and down, now at this point it can be either moving up or it can be moving down. We're going to start with the velocity at this point with it moving up. All right? This is its equilibrium position. It's oscillating back and forth. But at this position, if this is its equilibrium position, then its displacement is 0. Now I'm using y. You can use y or x. I'm using y because it's vertical motion. Okay? And we're going to say up is positive, down is negative for all of these, if you can remember that. So its y displacement is 0. The next position, next significant position, is when this mass gets all the way to the top and stops. So this position, the spring is compressed, and we have this mass, and its y displacement is some positive maximum value. Okay? Now, it doesn't stay at the top because what happens is there's a restoring force causing it to come back down. So this mass is going to come back down to its equilibrium position. So we have now a third significant position where the mass is back at its equilibrium position, but the velocity is going down. But its displacement is still 0, but the velocity is down. It's going to keep moving down until it slows down and stops at the very bottom. It's going to come back up. So we're going to have our fourth position. This spring is stretched until it gets to the bottom of its path here. And now this is y equals negative maximum value. It's displacement. And then it goes back up to this position, and then we're back where we started from. All right? So now let's take a look, and we're going to graph this displacement time graph. This is the displacement, this is the time, and we're going to assume each of these marks represents the equilibrium position. Okay, so let's take a look. We're going to start at equilibrium at this position right here. It's moving up, so the displacement time graph has to have a slope going up, and so reach its maximum value here, and then it's going to come back down to its equilibrium position. So they come like this. So this is position 1. This is position 2 at its highest point. This is position 3. And then down here is position 4. It's maximum negative displacement. So they come like this. This is position 4. And this is going to come back up to position 1 again. And that's one complete cycle. And it keeps doing this. It doesn't just stop there. It's moving up now. And we can just finish this graph. And notice we have a sine curve, or a sine wave. All right, now, that's displacement. Now let's talk about velocity. When is it moving its fastest? Well, remember, at the endpoints, that's where it stopped. So it's moving fastest in the middle. This is velocity is equal to some positive maximum value. This velocity here is equal to 0. This velocity here is equal to some negative maximum value. And this velocity is equal to 0 again. So now, let's draw the velocity time graph for this. Remember, the slope of a displacement time graph represents velocity, or we can use the information that we have here. At time t equals 0, this is time t equals 0, is velocity is a large positive value. So we have to start out large positive velocity, or we can look at the slope. The slope is a large positive slope. So this velocity is going to slow down. The slope is getting less and less and less. And then at this position, the velocity is 0. So it's going to look something like this. I'm sorry. Scratch that. This velocity is 0. So it'll look something like this. And then when it gets to this position right here, it has large negative velocity. And that slope is large and negative. Then come back up through here. Positive. It's just going to keep cycling through just like this. Let's take a look, see how that works. Again, this slope is large and positive, velocity large and positive. The slope here is 0, so the velocity has to be 0. The slope here is large and negative, so the velocity here has to be large and negative. The slope here is 0, so that velocity has to be 0. So we're oscillating back and forth that way. Positive maximum velocity, this is position 1. Velocity is 0, position 2. Velocity is large and, so let me do that again. This is position 1. This is position 2. This is position 3. Its velocity is large and negative. This is position 4. Its velocity is 0. Then we start oscillating again. Start over at a large positive velocity going up that way. Notice, for those of you that are in calculus, this is the first derivative of the displacement time. Now let's look at acceleration. Acceleration here, at the equilibrium position, the net force is 0. So if the net force is 0, the acceleration has to be 0 meters per second squared. The acceleration here, the net force is down. That's the largest net force that it has, so it has a negative maximum acceleration at this point. In other words, the net force is some negative maximum value. Here, the net force is 0 at equilibrium position. This acceleration here is also 0 because the net force is 0. The acceleration here is some positive maximum value going up. So now if we do the acceleration time graph of here, remember this is the first derivative of this, those are in calculus. The acceleration time graph is the second derivative of this displacement time graph. So notice the acceleration is almost the opposite of the velocity. So this slope here, this velocity, is actually 0, so the acceleration is 0. The acceleration velocity time graph is the acceleration. This slope here is large and negative, so the velocity at that point is large and negative. The slope here, the velocity time graph, is 0, so the acceleration is 0. And we just keep going. The slope here is large and positive, so the acceleration is large and positive. The slope here is 0, so the acceleration is 0. So we just keep going. So this is the acceleration time graph. Looking like this. Okay. Now let's keep going for some other things that we know. Whoops, I'm sorry. This acceleration is 0. We got this we got all the acceleration. Now let's go back and look at potential energy. The potential energy at this position right here, this is the potential energy of the spring, so to speak, is 0. It has its greatest velocity there, so its kinetic energy has some maximum kinetic energy. Its potential energy here is some maximum value potential energy, and it has no kinetic energy. Kinetic energy is 0. So what happens is all this kinetic energy is converted to potential energy here, and then this potential energy here is going to be converted to kinetic energy. Again, we have some, maximum kinetic energy at equilibrium position because that's where it's moving the fastest. And we have 0 potential energy. The kinetic energy here is 0, and the potential energy is some maximum value. So we have all these different things that we can analyze for simple harmonic motion: the displacement, velocity, acceleration, potential energy, and kinetic energy. All right, so let's take a look at some things here. Which of the following statements are true at some point during the course of the motion? Explain. I want you to pause the video and see if you can answer these questions. All right, so pause the video, answer those questions, then come back and take a look at the answers. All right, let's take a look. 0 velocity and non-zero acceleration. Is this true or not? Or can this happen? Can this simple harmonic motion, this mass moving on a spring, oscillating up and down, can it have 0 velocity and non-zero acceleration? Yes, it can. The positions, position 2 and 4. Let's look at position 2. It has 0 velocity and non-zero acceleration. It has a maximum acceleration. And also position 4. has zero velocity and some non-zero acceleration. Zero velocity and zero acceleration. There are no places that have that. We have zero acceleration and non-zero velocity. Yes, those are positions 1 and 3. Because position 1 has zero acceleration and some velocity. Position 3 has zero acceleration and some velocity, maximum velocity actually. It can have non-zero velocity and non-zero acceleration. Yes, it can. Anywhere except position 1, position 2, position 3, and position 4. Remember, position 1, 2, 3, and 4 are only 4 spaces or 4 points in this oscillation. At any other point, it has between those maximum values. Okay, so anywhere except 1, 2, 3, and 4. Let's summarize a couple of things here. Simple harmonic motion is any vibrating system for which the restoring force is directly proportional to the negative of the displacement. In other words, F equals negative kx. Any system that has that quantity, if we graph this, this is force, this is x, this is F, this is x, we get a linear relationship. Or if this would be if we ignore the negative, if we include the negative, it'd be some, oops, sorry, this is force, this is displacement, it would look like this, okay? So let's take a look, see if we understand. Circle the equations that are examples of simple harmonic motion. Explain why you circled or did not circle each equation. Remember, pause the video, see if you can answer this, but remember, the equation must be the form F equals negative kx. In other words, there must be a constant. This x must be a linear relationship with the force. So see if you can answer these. Pause the video and answer which of these follow the simple harmonic motion rule. Then when you get done, start the video again and see if you're correct. This is no, because this is x squared, not just x. This is correct. 2.3 is the constant. Y is the displacement, and it's a restoring force. This is technically not correct because it's not a negative restoring force. This is correct because it's negative 4.7. That's the constant in x. And this is also correct. This is because this is a displacement, except this is an angular displacement, theta. Because remember, the sine wave, in a sine wave, there are 0 degrees, 90 degrees, or there are angular functions that relate to a sine wave. So this is just a measure of displacement, except it's angular displacement, but it's still a displacement. So this is also true. All right. Go back through and look at the instructions for the rest of the day and see what you need to do.